This is today 3D graphics look. Narrow view and very jagged edges. And this is what happens when somebody tries to render the view with the wide angle. Linear distortion happens. Now let me show you the future of 3D graphics, a new rasterizer that can render the view in unlimited distortion and in an unlimited field of view, meaning that it can display graphics in 360 degrees directly from the model data to the pixels on the screen, without any additional steps. It can also do unlimited number of individual views from the same observation point, like here you see VR lens distortion, individual for each eye, without any impact on performance. Or double paraboloid reflection map. It can also do projection mapping, useful for virtual film production, and also this crazy 64 individual equirectangular views, without any impact on performance. Now there's more. I mentioned the jagged edges. Now look, they are gone. This is a new anti-aliasing technique, comparable in visual fidelity to multi-sampling times 32 or even 64. But this is not post-process, but a rasterizer feature. And it has no multi-sampling. There's only one sample per pixel. Sounds impossible? Well, it was described in the paper Temporally Smooth Anti-Aliasing and as distortion with rasterization map, available at Arxiv, under the license. This paper goes through all the details of the anti-aliasing technique, as well as the rasterization. It also presents some GLSL code, so one can verify my statements. Now let me show you how this all works. This rasterizer uses so-called perspective map, which is a texture that defines camera parameters, distortion parameters, as well as screen shape. It can, for example, display 5 screen array at once, where usually application would have to render 5 separate views, stitch them together, which would make it run 5 times slower. Here everything is rendered at once, so there's no impact on performance. Let's see one more. Now the obvious use case would be VR. Nowadays, to render this view, computer has to go through few steps. First, render the rectilinear view, which is the only one it can do, to the bigger render target than the screen resolution. Then distort the view, leaving black borders of pixels that are processed but invisible, and lowering the image quality by supersampling and undersampling some pixels. With my new rasterizer, VR view can be rendered directly with the lens distortion, with 1:1 resolution, and additionally with extra anti-aliasing. This basically omits all the additional steps, which makes the VR game run same fast as the desktop app, which is very useful for mobile applications or console VR. Another use case is virtual film production, where movies are not shot on the green screen, but giant LED screen, which displays real-time graphics generated in Unreal Engine. But to display the final pixels, Computer has to go through a few steps. First, render a multiple view of the scene, stitch them together, and map them on the screen, which requires the bigger resolution of the initial rendered target. With my new rasterizer, 3D graphics can be rendered directly onto the pixels of the LED screen. With distortion and no additional steps, which greatly would reduce the costs. Another use case is simulating driving for self-driving cars, AI training, where the onboard camera view could have fisheye distortion like the real one. And of course, the anamorphic lens distortion simulation with some additional steps could be performed. Nowadays, to merge CG graphics with the camera footage of such lens, the CG image has to go through the process of rotoscoping, which is adjusting the distortion frame by frame by hand. This would also greatly reduce the costs. Now, to implement this technique into production, one has to change the graphics pipeline. Here is the OpenGL graphics pipeline with those purple boxes representing fixed functions that are defined in the silicon of the GPU. To implement unlimited distortion, unlimited field of view, and unlimited number of views, one has to change the rasterizer function, which means changing the graphics standard and GPU architecture. To also implement the anti-aliasing, one has to change additionally the output merger and sort the polygon data prior to rasterization, like in the days of PlayStation 1. This is just scratching the surface of this topic and this technology and all the possibilities that it brings. So I invite you to talk with me about this future. And thank you very much for watching this video. Jakub Max Fober.